Hello and good Monday morning. Hopefully, you guys are doing well. You had a nice weekend. I didn't have a great weekend. I hurt my back on Thursday, so I spent the whole day in bed Friday. Saturday, I was able to get out and walk around with crutches, and then today I was able to just barely walk around. So, anyway, getting better every day, so that's good news for me. It sucks though when you hurt your back. You don't really appreciate your health until you lose it. So anyway, enough about that. Today's lesson, we're going to review equilibrium ice tables. So what I'm going to be doing is I'm going to go through 2 examples in your study guide, and then I'm going to assign 4 other ones for you to work on. And then I'm also going to introduce you to Le Chateliers principle. And it's a very short lesson on that. And then we're going to go into it in detail tomorrow. This is only a 4-day week for you guys. If you've read the weekly memo already, you'll see that we're just doing lessons Monday, Tuesday, Wednesday, and then a quiz on Thursday and no school on Friday. And then I believe next week on Friday, there's something going on for grade 12s. I don't remember. Oh yeah, grad. So there won't be any classes next Friday as well. I think they're still figuring out what we're going to do to honor and celebrate you guys. But great minds are at work, so hopefully they'll come up with some great stuff for you. Okay, so we're in page 345 of your study guide. The assignment that you're going to be working on is page 344, 345, 346. And there's 6 questions, and I'm going to go through 2 of the more challenging ones. Just going to flip this around so I can write on it a little better. So I'm going to go through 2 of them with you. You can just fill these in right in your study guide if you would like. Okay, so what have we got here? For the following reaction, it's 600 degrees Celsius. So that means that the equilibrium constant is only valid at that temperature. Okay, so we've got our reaction. 2 moles of SO2 gas react with 1 mole of oxygen gas to make 2 moles of SO3. It's in equilibrium, moving back and forth. Okay, so I'm just going to rewrite that equation. 2 SO2s gas plus O2 gas gives us 2 SO3 gas. By the way, I hope you guys, if you live with your mom, I hope you spoiled your mom today for Mother's Day. I know my daughters did. Oh my gosh. I just realized I forgot to call my mom. Darn it. It is like 9 o'clock at night. I totally forgot. Ugh, I'm going to have to call her right after I record this lesson. Ugh. Okay. How's that for embarrassing? All right. So ice table. I, C, E. Let's organize the data. 2 moles of SO2, and it's in a 1 liter flask. So that means 2 moles per liter, 2.00 moles per liter of SO2, 1.50 moles per liter of oxygen, and 3.50 moles per liter of SO3. So we have all of our initial concentrations. And when equilibrium is reached, we have 4.5 moles of SO3. So going from there to there, it looks like we gained SO3, we gained product. So that means this is a gain on the product side. The 2 in front means we gained 2 amounts. If we're gaining product, we are losing reactant minus, and there's a 1 there, so minus 1x and minus 2x. So both reactants are decreasing, products are increasing. Add up the top 2 rows to get the equilibrium concentrations. 2.00 minus 2x, 1.50 minus 1x, 1.50, and we already have that concentration. Okay, so now we just need to solve for x, and we have it right here. We know that if we add up 3.50 plus 2x, that adds up to 4.50. So rearrange and solve algebraically, and we find out that x is 0.50. Okay, so now I can substitute that back into this. 2.00 minus 2x becomes 1.00. 1.50 minus 0.5 is 1.0. Okay, There are my 3 equilibrium concentrations. Done. Determine the value of Kc. Okay, so to figure out the equilibrium constant, we need to write the equilibrium law expression. Products, and that's squared because of that coefficient, over reactants, constant equilibrium concentration of SO2 squared, and equilibrium concentration of oxygen. And we have all 3 of those equilibrium concentrations. So products is 4.50 squared over 1.00 from here, and it's squared times 1.00. Okay, well, that's interesting. The bottom is just going to be 1. So 4.50 squared is, where did I put it? 4.50 squared is 20.25, and we'll go 3 sig digs, 20.3. Okay, so there's our equilibrium constant Kc, 20.3. So that's one type of equilibrium question using an ice table where you are graphing. No, sorry, we're not graphing. We solve for x because we had one of the 3 equilibrium concentrations and then calculating the equilibrium constant. Okay, the second one I want to do is number 5. So let's take a look at this one. Same reaction. 2SO2 gas reacts with O2 gas to produce 2SO3 gas. And what are they giving us? 2 moles of SO2. And that's in a 1 liter flask, 2 moles per liter. That's our initial. And 2 moles per liter of SO3. And an unknown amount. Oh, this is different. So it's not 0. It's unknown. We're going to call it Y, not X, because we'll use X for our change in the change column. Okay. What do we know here? At equilibrium, the SO3 was found to be 1.80 at equilibrium. So we went from 2 to 1.8. So that's a loss. We lost 2 amounts, and that's coming from there. Okay, we lost 2 amounts. So 2 minus 2x adds up to 1.8. So we could actually solve for x. 2 minus 2x equals 1.8. So x is 0.10. Okay. What have we got going on here? For losing product, we are gaining 1 reactant there and gaining 2 reactants there. Okay, so at equilibrium, we have 2 plus 2x and y plus x. And we already know x is 0.1. So this becomes 2.20, and this becomes y plus 0.10. Okay, if we look at these, we have this equilibrium concentration, this one, and this one. And it's the same reaction. We have the equilibrium constant right there. So we can graph this one and solve for our unknown. Let's put it over here. Okay, so Kc equals 1.30. So our equilibrium expression is concentration of SO3 squared over concentration of O2 times concentration of SO2 squared. Okay, so I'll substitute those in. SO3 is 1.80 squared divided by O2, which is Y plus 0.1. And do double brackets, make that one a square. And this one is 2.2 squared. 2.20 squared. Don't forget that squared from there and from there. Okay, so now I can graph it and solve for the intersect. Solve for intersect by graphing. So when I put it in my calculator, I'll just call x, y, so that I have that same x variable. So in my calculator, y1 will be 1.30 and y2 will be 1.80 squared divided by x plus 0.1 times 2.20 squared. And I'm just going to make sure I got all that written down correctly. Yes. Okay. Graph it, and you get the x-intersect is 0.415. I'm running out of space, so I'm going to have to jump down here. Okay, so now I know that this equilibrium concentration will be 0.415 plus 0.10, 0.515. Now, just for fun, if you wanted to see if you did this right, you could go back to our equilibrium constant and you could plug in all the three concentrations. So 1.80 squared over 2.20 squared times 0.515. Those are our three equilibrium concentrations, and you get 1.3. You go, okay, I must have got the right answer because the equilibrium concentration is 1.3. So you can do a little double check if you have time to make sure that you did indeed solve for all three equilibrium concentrations correctly. So those are tricky. I think those are the hardest ones when you have to solve for an initial concentration. So now I've shown you all the types of ice tables and different equilibrium questions. So I would like you guys to finish off numbers 1, 2, 4, and 6 on these same pages. So that's number 1. That shouldn't take you too long. And then the second thing we're going to do is just an introduction to Le Chatelier's principle. And this is in your study guide. The notes for this are found on page number 312. We're going to go through it in detail tomorrow, but I'm going to give you the sort of simple version today. So Le Chatelier was a French chemist, and his principle or his statement is the following. When a chemical system at equilibrium is disturbed by a change in a property of the system, it always appears to react in a direction that opposes the change. So it does the opposite. So for example, if I add a chemical, it will try and use up that chemical. If I remove a chemical, it will try and replace that chemical. What it's trying to do is get back to the equilibrium concentrations. Okay, this is what chemical systems do. They want to return to their natural equilibrium position. So when you disturb it, it opposes the disturbance and tries to reverse and get back to the original concentrations. Sometimes I use a teeter-totter analogy. So here is our chemical reaction that we were just looking at, and I've put it on a fulcrum so that it can pivot. So if you think of this as a teeter-totter, if I were to increase the amount of oxygen, so if I added extra oxygen, the teeter-totter would go down. It would be disturbed. How could we get the teeter-totter back to level? So it's like you've added extra weight on the reactant side and it's sunk down. How would we get this thing to level out again? We would have to shift it forward to move some of the reactant to the product side. If we use up some reactant and gain some product, the product side becomes heavier, the reactant side becomes lighter, and it gets back to equilibrium. So I add reactant, it moves forward to use up the reactant. So this statement says, if we increase the amount of oxygen, the system will decrease oxygen by moving forward. By the way, it will also decrease some SO2 because both reactants will get used up when it moves forward. Okay, let's look at the next one. If we increase the energy or raise the temperature, so here's temperature. When you do energy questions, think of energy as like a chemical compound. So if I were to increase or add more of this compound, it would try and use it up. How would it use it up? It would go in reverse. So if I add energy, it will increase the temperature, it will decrease the temp by moving reverse or backwards. Add something, it moves away from it. Okay, what if we decrease the amount of SO2? So let's switch colors here. Blue. So SO2, if we remove SO2, the teeter-totter drops, the teeter-totter goes up. We have to move in reverse to replace the SO2. So if we decrease the amount of SO2, the system will try and increase the SO2 by moving in reverse. Okay, so far so good, I hope. Now we're going to do our last one. These are the tricky ones. Pressure. If we increase the pressure in the system, it will try to decrease the pressure. How? Okay, this one's tricky. So I'm just going to get rid of everything on here so we can take a look at this. Pressure in a chemical system is due to collision of molecules on the chamber walls or the walls of the vessel. So right now, if we look at this, there is 2 moles of gas and 1. So this side has 3 moles of gas. This side has 2 moles of gas. So if we have 3 here and only 2 here, we call this the high pressure side. There's more collisions. And this is the low pressure side. There's less collisions because there's less molecules of gas. So if we increase pressure, it will try and decrease pressure. How does it decrease pressure? By moving to the low pressure side to decrease pressure, moving forward. So for pressure questions, you have to count the moles of gas and figure out your high and low. So it's just that one extra step. Okay, we're going to just pause for a second here. I'm going to jump to a video with Professor Dave, and he's going to sort of review this as well. He's got nice animations, so let's take a look at this.
Relieve that stress. So let's see some examples of a stress we could put on a system at equilibrium. First, we could modify the concentration of any of the compounds. Let's say we add some of this reaction. That will unbalance the equilibrium, and the forward reaction will speed up to use up some of the additional reactants, turn them into products, and restore equilibrium. The equilibrium is said to have shifted right. If we add more products, it would shift left. Likewise, if we selectively remove one of the components, the equilibrium will shift to produce more of that species to restore balance. That is one type of stress we could put on a system. Another stress.
So I'm just going to jump ahead a little here because he goes through a bunch of info you don't need to hear. There we go.
In that scenario. Once we translate thermochemical data in this way, we can treat the word heat as just another substance involved in the reaction. Higher temperature means more heat, so things will shift to the other side to use up some excess heat and relieve the stress. Cooling it down would have the opposite effect. The third stress we can examine is changing the volume or pressure. Let's say the equilibrium involves gases in a balloon. What if we decrease the volume? If we remember Boyle's law, we know that the pressure will go up. Since the smaller the volume, the more the particles will hit the sides and exert pressure. If there is a discrepancy in the number of moles of particles on either side of the equilibrium, it will shift towards the side with fewer particles so as to alleviate some of the additional pressure. In this equilibrium between a diatomic molecule and two monoatomic species, the right side has twice as many particles. So shifting left means atoms fusing together, resulting in fewer particles, which lowers the pressure on the container. If we increase the volume, thereby lowering the pressure, the equilibrium would shift towards the side with more particles in order to regain some of the lost pressure. Let's check comprehension.
Okay, so if you look at this slide, which way will equilibrium shift if more hydrogen is added? Okay, more hydrogen is added. So that's on the product side. If we add hydrogen, Le Chatelier says it will try to remove hydrogen by shifting reverse or left. Okay, what if oxygen is removed? So if we remove oxygen, it will shift forward to replace it. Temperature increases. So this one's tricky. So temperature, delta H is positive 187. That means it's endothermic. So temperature would go on the reactant side. So if we increase temperature, it will try and decrease it by moving forward. And then the last one, volume is reduced. If you reduce the volume, you increase the pressure. So if the pressure is increased, Le Chatelier will decrease the pressure. Which side does it move to decrease the pressure? Left, because the right side has 2 moles of gas, and that would be the high pressure side. Okay, let's jump back to here. And I have one more slide for you. Okay, this one's kind of, actually is very interesting. So we'll just talk about this quick. Dinitrogen tetraoxide is a colorless gas. Nitrogen dioxide is reddish brown. In cities, when your vehicle burns gasoline, it also combusts some nitrogen and produces nitrogen dioxide. So that comes from cars. This is what creates smog, rush hour smog. So if you drive into a city, you'll often see that reddish brown haze over Calgary or Edmonton, and that's due to the nitrogen dioxide. Now, what happens is in the morning, when the sun first comes up, it heats up the air. It adds energy. So which way would this system shift in the early morning when the sun rises and starts to heat the system? So Le Chatelier says that if we add energy or add sunlight, it will try and use up the energy by shifting forward. And that's why you see smog in the morning. Driving in an early morning rush hour, smog always looks worse. In the evening, as the sun sets, we are removing energy. The air is cooling down. If we are removing energy, which way will the system move to try and replace the energy? Right. And so the smog disappears and the air becomes colorless in the evenings. Okay, second example, very interesting and very relevant. Carbon dioxide gas in the atmosphere combines with water to make carbonic acid, H2CO3, which can dissociate into acidic H plus and HCO3 minus. So the relevance of this one is with global warming, as we're adding more carbon dioxide gas into our atmosphere, which way are we pushing this system if we are increasing CO2? The system will try and decrease CO2 by moving forward, which is making more acid. So the oceans on Earth, our liquid water oceans, are becoming more acidic as we increase the CO2. And this is a huge problem because lots of organisms in the ocean have shells made of limestone, calcium carbonate, which is a base. So organisms with basic shells that are in an acidic environment are losing their shells and dying. So we're seeing pretty large die-offs, and there's just lots of other species that are sensitive to low pH or acidic levels. So as the oceans become more acidic, we start to see major disruptions to the ecosystems and the food chains. bleaching of coral reefs, loss of limestone shells. There's just all kinds of major catastrophic problems due to this equilibrium shift because of us and fossil fuels. Darn those fossil fuels. I'm telling you, if you could figure out a way to pull CO2 out of the atmosphere and put it into a solid form, you could save our planet. Okay, so to work on the Le Chatelier, I would suggest you try this worksheet, and especially numbers 1 and 2. It's pretty short. It'll only take you about 5 to 10 minutes to do numbers 1 and 2. And then you are also going to work on those 4 questions from your study guide on page 344, numbers 1, 2, 4, and 6. And that's it for today. Okay, you guys, have a wonderful afternoon. I got to go call my mom and apologize for forgetting to call her on Mother's Day. I have 2 other brothers, and I guarantee you they've both called, which makes me the black sheep of the day. Darn it. Okay, have a nice day, you guys. Talk to you tomorrow.